the era of 1-bit LLMs. So yeah, that's where we're at now. We're training large language models on 1-bit precision, or rather 1.58 bits, because they use ternary, not binary, -1, or -1, 1, and 0. So ternary. And they do that, they basically store a weight matrix in using -1, 0, and 1 instead of a weight matrix full of floating point numbers. And yeah, that's quite cool that you can train a whole language model on just with weight matrices of just -1, 0, and 1. Not only that, since you can represent it, the weight matrices using -1, 0, and 1, all the matrix multiplications essentially become additions, which is quite interesting. So yeah, it'll be interesting to see if this scales well, because I think they only put this on like 4 billion, but it'll be very, very cool if this scaled to like 70 billion. This paper here, The Era of 1-Bit LLMs, is the paper basically everyone's seen. That one doesn't introduce much theory. What does is BitNet. So BitNet is a paper from 2023, which introduces all the theory for this. So yeah, this one has a lot more theory in it. So yeah, why would you want a 1-bit precision? Why would you want 1-bit precision weights? Well, you always want lower precision, or it's always nice to have a lower precision if you can get the same results, because it essentially is faster to compute. If you think about it, if I have to add two numbers, essentially you have to add both 16 bits together in some way, or you have to add both 16 bits together using an adder, while 1-bit, it's just one operation, add the 2 bits. In a 16-bit operation, you have 16 bits representing it, and you have to do 16 operations on that instead of just one. And it's actually more than 16 operations, but essentially on that order. So yeah, it's nice because you do a lot less operations, which implies that it's going to be faster, because every addition, every multiplication, every operator is going to take a lot less time to do and a lot less compute to do it. It also takes a lot less memory, obviously, because you store your weights as ternary. So let's say you store it in 4 bits, because you can't store ternary well, or at least I don't know of a way to store it well. So you essentially store it, or not 4 bits, 2 bits, so 4 values. So 0, 0, 0, 1, 1, 0. So you can represent that as -1, 1, and 1, or -1, 1, 0, instead of 16. So that's a factor of 8 that you're reducing it by. So quite a bit of memory that you're saving whenever you're storing this. So a lot of memory gains, speed gains, and if you can do this with the same accuracy, then there's no reason not to do it. So what is their approach? They essentially take so in your transformer, you have a transformer block, and your transformer block consists of a layer norm, and then you have your attention mechanism, and the attention mechanism consists of 3 layers. So this is where all the parameters reside. And then you have another layer norm, and then you have a feed-forward layer. And then you have your output. So this is just a normal transformer block. And all your parameters essentially come from here. Your feed-forward layers, I'll make that linear layer. So most of them actually come from this one, because this is such a massive linear layer. But yeah, essentially your parameters all come from linear layers. So it would be nice if you can change these linear layers from floating point 16 to just 2 bits. So 1, floating point 1, I guess. Sure, we'll go with that. So yeah, floating point 16 to floating point 1, so binary. And that's what they do here. They essentially take that and they convert it to -1 and 1. And what they're going to do is, so this is our feed-forward layer right here, and this is our attention mechanism right here. So essentially, for all the linear layers, they're going to replace it with something called BitLinear. No, and I forgot about the output linear layer. Sorry. So you have 4 linear layers for attention, whatever. So yeah, you have your feed-forward, and you have your multi-head attention, and you basically want to replace that with BitLinear instead. So that's the idea. And BitLinear is this thing here. So this is what is the heart of their algorithm, and this is what we're going to be going through. So the first thing is what is a linear? So a linear layer is just y is equal to xw or wx, however you want to write that. And what we want to do is take our weight matrix and convert it to floating point 1, I guess. I'll call it that. Still sounds ridiculous in my head. And our x, so this is going to be a floating point 16 weight. We're going to convert this to floating point 8. So you essentially keep x in floating point 16 because you need high precision for your inputs. So like your vectors here, your vectors representing some word, cat. This needs to be high precision because you're storing it in some high dimensional space, and the precision matters in that case. It also matters in the output because you want to find you want a distribution, and you want the distribution to be quite obvious which word is next. And to do that, you need high precision. So they actually don't quantize the output projection in the transformer, because if you quantize that, then your distribution is going to be all messed up. So you want high precision still for your input x, for your activations. So they only quantize x from floating point 16 to floating point 8, but they quantize the weights, and they quantize the weights to floating point 1. Unfortunately, they don't quantize everything. That would be very weird, having this as a -1, 1. But yeah, floating point 16 to floating point 8, and this floating point 1. So essentially, you're going to have a quantization step. Forget about layer norm. So you're going to have multiple steps. You're going to have your floating point 6 inputs, your x, and then you're going to have your apps max quantization, which will convert this to floating point 8. And you have your 1-bit weights. So these are stored in floating point 8. And on the fly, you quantize them to while you're training. While you're training, you quantize these to 1 bit. So I guess floating point 1. I'll write that here, floating point 1. And you do this multiplication, which is actually just an addition, which we'll see later. But you can essentially think of this as just a matrix multiplication between between these weights and these quantized values here. And you can do some tricks in memory for this being 1 and this being floating point 8. I guess you can cast this to floating point 8 if you wanted to. But anyways, you do a matrix multiplication, so that results in a floating point 8 output, and then you have to dequantize it to floating point 16 again to get your output in full precision. Why? So that's the matrix multiplication that's being done here. So the first step is we have these floating point 8 weights, which we initialize using normal initialization techniques, and we want to quantize it to -1, 1. Essentially, what you're looking for is a random matrix. So you want your floating point 8 matrix, and you want to initialize it in such a way so that there's probably an even amount of -1s and 1s, so that it's quite random, and you want those to be randomly distributed among your weight matrix, and that's how you want to initialize it. So the way they quantize the weight matrix is quite simple. You have your weight matrix. This is our floating point 8 matrix. And you subtract the mean. So this just centers it, and then you take the sign of that. So essentially what this is doing is you have your distribution here. So I am going to assume Gauss because I guess you can with weight matrices. I'm going to assume Gauss. So assume Gaussian for your weights, which is an assumption you can actually make. And it has some mean here. So it has some mean alpha. And let's say this is at some step during training, and this is 0 here. So what you want to do is center it. So you take it, you center the distribution, and then you take the sign. So all of these here will be -1, and all of these here will be +1. So that'll be your plus and -1. So essentially all you're doing is moving the distribution and basically getting an even amount of -1s and +1s for your quantization, basically getting the most out of your quantization. Because if I had this here, this would essentially give me all +1s, and I would just have a matrix of +1s, which is kind of useless. So that's why you center it first. So then you can get the an even amount of -1 and +1. And they do that by just saying they take the mean. Oops. They take the mean of the weight matrix, and then they just take they subtract by it, and then they take the sign here. So that's all. That's all you're doing, and that pretty easily gives you your 1-bit quantization with an even bin size for both. Real quick, mentioning quantization. The goal of quantization is to basically get the most out of lower precision as you can. So let's say I have this here, which is in some precision with 6 buckets. You can think of floating point 16 as having 2 to the 16 buckets. Actually, I think it's 2 to the 16 minus 1 buckets. You can think of it in that way. So quite a bit. In this case, I have 6 here, and in this case, I have 3, and we want to quantize to this. So to get the most out of this, what you would do is say, take the first 2 elements and assign that to the first element in your quantized state. Take the next 2 elements and put that in the second bucket, and then the last 2 elements and put that in your third bucket. So if this was our range of possibilities for a higher precision, and this was our range of possibilities for lower precision, we essentially want to assign it as evenly or as uniform as possible, because I could just as validly do this, where all of them are, where the first 4 are assigned to the first one, this is assigned to the second one, and this is assigned to the third one. This is a bad quantization because you have 4 elements in the first corresponding to the first element, which isn't good because then you don't get, it's not as expressive as it possibly could be. So essentially a uniform assignment. And this is what they're going to do. I mean, this is what you see here. You have a uniform assignment among -1 and +1. And that's what they're going to do here with x. So you basically want to have a uniform assignment from floating point 16 to floating point 8. So the way they do that is with this formula here. So it looks complicated. It isn't that complicated. So imagine I have a matrix X, and the matrix X has a maximum value, a absolute maximum value. So apps max of A. We'll just call this A. And that would mean that your values, actually I'll call it alpha because I feel like having a Greek letter there. So yeah, this is our range for X, and X is just some intermediate activation state. So in your transformer, you're going to have some activations here, here, and here, and here. So it's just some intermediate activation. You basically don't assume very much about that. You assume that you know the alpha, you know the min and max because you can get that, but you can't make nice assumptions like you can with like the weight matrix because it changes all the time. So you basically have your negative alpha and your positive alpha, and what you're going to do is multiply by this. So so you're essentially going to multiply by Q and scale by gamma. So negative alpha is multiplied by Q, QB, and divided by gamma, and then you're going to have alpha times QB divided by gamma. So your min and max, all your values are going to be divided by or multiplied by this term here, QB over gamma. What matters is your min and max mostly. So if we look at this, they define QB to be this up here. So QB is 2 to the b minus 1, and this is essentially your range for whatever floating point, or for whatever your precision is. So for floating point 8, your QB is equal, or I guess this would be Q8, is equal to 128. And for floating point 16, your Q16 is equal to, it's like 32,000 or something like that. Yeah, so floating point 8, floating point 16, and this is essentially your range. So you can do negative QB to QB there. And this is your range that you want to put your values into. So we essentially want to convert this from 32,000, a range of 32,000 to 128. And you do that by just multiplying by QB and dividing by gamma. And gamma over here is defined as the absolute max value in X. And we define the absolute max value as alpha. So gamma is equal to alpha, which gives you negative alpha times QB over alpha, and alpha times QB over alpha, which results in negative QB and QB, which is what you want. And then you just clip that for stability in case there's some rounding issues. So yeah, you basically have this as floating point 16, which is in the range of 32,000, like plus and minus 32,000. And then you convert it to floating point 8. Oh, it's still floating point 16, but it's in the range for floating point 8, 128. And then what you can do is you can cast this. So cast from whatever, from floating point 16 to floating point 8. And you can just, you just do that by casting. But now that it's in the range, you won't have casting issues. It should be quite simple to do that. Yeah, and this is just clip. So clip between two values. So yeah, that's quantizing this from floating point 16 to floating point 8. So we now have our quantized states for both of these. Now what do you do whenever you quantize them? You just multiply them. So you have your weight matrix here and your input activation, your quantized input activations here. So just a normal matrix multiplication. That's it. Now they add this layer norm here for a specific reason. And it's because it has nice properties whenever you do the dequantization. So they mention that here. They say, to preserve the variance after quantization, we introduce a layer norm function before the activation quantization. One thing to note is this is not layer norm. This is, or layer norm in the sense that you would expect. So layer norm usually is divide by the mean, subtract by the standard deviation, multiply by some value gamma, and maybe we'll add alpha there. And gamma and alpha are learnable parameters, I think, in RD. So this essentially gives you zero mean and one standard deviation for X. It basically puts it in it basically centers the distribution and it gives you one standard or a standard deviation of 1. This will shift the standard deviation to not be 1 unless gamma is 1, and this will shift the mean to not be 0 unless alpha is 0. So they remove this part because you want to have 0 mean, 1 standard deviation for the assumptions they're making. So layer norm is not a layer norm layer. It's just this. It's just normalizing. They say that here. Subtract by the mean, divide by the standard deviation. So it's not a layer norm layer. Anyways, they say in this way, the variance of the output y is then estimated as the variance is approximately 1, which has the same magnitude as the full precision counterpart, the variance of y. In the context of transformers, it has the exact implementation as sub-ln, where sub-ln is and the quantization methods above, they have BitLinear, which is formulated as this. So essentially, if you add a layer norm, it gives you nice properties which allow you to dequantize it in this way. So since they say it preserves the 1 variance, it allows you to do this. So we have our X, we put it through layer norm, and then we quantize it. So that's that, and then we multiply it by W. So this is just our matrix multiplication here. Now what we want to do is dequantize this so that we have this back in floating point 16. So we want to convert it from floating point 8 to floating point 16. Now one thing to note is if we have something in floating point 8, so let's say I have 3 values here, and I want to map back to the 6 values I had before, you obviously have a loss, that's 6, not 5. You obviously have a loss of precision. So this value could be mapped here, or here, but it can't be mapped to both. I guess it could be mapped to both, actually. But you obviously lose precision because these two elements are not unique. They basically correspond to this one, these two correspond to this one, and these two correspond to the last one. So whenever dequantization, you lose precision because you're going from a smaller space to a larger space, essentially. So there's obviously going to be a loss of information. Evidently, that information is not as important as one might think. The precision can just be, you can do this and it works well. And they've shown empirically. And this is what's normally done with quantization. So normal loss of information that is, you don't have to be as fine-grained as you would expect. So basically going from floating point 8 to floating point 16. So yeah, this is floating point 8 here, the output of this. And what we're going to do is essentially reverse what we had before. So if we look here, this is Q over gamma. Here is not Q over gamma, it is gamma over Q. So if we look here, we have gamma. So this is essentially us dequantizing the input x, or rather gamma over Q, because we did Q over gamma to essentially give us the, Q over gamma to quantize it, then you can do gamma over Q to dequantize it. If we look here, if we're in this state here, and alpha is we're in this state here, then what you do is you multiply by, so negative QB. So this is our state we're in. This is the quantized state. Then you multiply by gamma over QB. And QB times gamma over QB. And these cancel, and that gives you negative gamma and gamma. So this basically brings you back to the values you had before. And yeah, this would be plus and minus, or negative alpha and alpha, because remember, this is just our absolute max. And then you can cast this to floating point 16, of course with the loss of precision, because you casted it to floating point 8 here. So yeah, that's essentially just the reverse operator. And B is basically, so remember the weights are stored in floating point 8, they're quantized. This is essentially unquantizing the weights, you can think of it that way. And B is just the average absolute value of the weights. So you can think of this as basically dequantizing the weights, because this thing here, this thing is not just x, it's x multiplied by w, so you basically have to dequantize both the weights and the inputs, and that's why they do both these here, so beta and gamma, not just gamma. But yeah, it's just dequantizing it, essentially. And yeah, that is the BitLinear part. You basically just quantize it, quantize the weights, quantize the activations, multiply them together, and then dequantize it, and yeah, there you go. You have your BitLinear. Yeah, so they mention this group part here. So this group part here, model parallelism with group quantization normalization, is important. So if you've ever messed with memory, a very annoying thing you'll find is doing a collective sum, a reduction is it's much slower than one might think. So if I have a matrix here, and I wanted to do a reduction here, so do that. So I want to do a sum reduction, which is essentially what you do, or some sort of reduction. So you basically have a reduction over W here, which is just sum over it. So a reduction is basically just you're taking your matrix of values and you want to convert it to one value by summing everything to one value. Here, it's a reduction because you're looking for the maximum value. So you basically have to scan every single value again. Here, you basically have to do, this is also a reduction. So there's a problem because reductions are very slow in memory. So if I have this here, let's say I assigned a thread to each part of this. So T0, T1, T2, T3. So a naive, and I want to do a sum over all these elements. This is just 4 by 4 elements, and I want to do a sum. So a naive approach is to say, well, the sum is going to be equal to just t0. So the sum is just going to be t0 summing all the elements. So I'm just going to say, okay, t0, you're going to sum every element in here. So it's going to say for I in like the range from 0 to 4, and we'll do 0 to 16. So we'll flatten this to just be 16 values to make it easy. And then it just sums it. So you have your sum equal to 0, and then it does sum plus equals whatever your matrix of I. So naive approach. And thread 0 does this. The problem is you have all of these threads here waiting and doing nothing, and that this is slow. This takes the amount of time it takes to do this is the size of your weight matrix or the size of your activation, so it's very slow to do this. Now, another thing you could do is say, okay, well, if I want to parallelize this, then I can have, say, T0 do these first two elements. So T1, T0 will be the sum of T0 and T1, and then T2 will be the sum of T2 and T3. So essentially this element, or this thread is not going to be used, and this thread isn't going to be used. So every other thread is not going to be used. So you can do these in parallel because it's it's threaded. So it does this part in parallel. So this only takes one operation, and you have, or essentially order one time, and you essentially have these partial sums. And then you say, okay, T0 is then going to sum this element. So this will be T3 and T2, and T0 and T1. So it'll take this partial sum from T2, and it'll add it to itself in T0. And this element will also do that, and this element will also do that, and this one will also do that. So then in the second step, you have these threads doing nothing. So this whole block here doing nothing. And then you keep on doing that. So then this would send information to T0, and then this one will send information to T0 until you basically could create this tree until T0 has all the information. So this is faster. It's an order of log complexity, which is better than linear complexity, and more threads are doing stuff, but it's still very slow in memory because you have all these threads waiting doing nothing, and you never want threads doing nothing. So what they do, or all that to say, a reduction operator is slow, and what you want is you want parallelism. So the way they do parallelism is quite simple. You can basically break up your matrix. So like I said, we want to do a all reduce. So we want to reduce all the elements in here. And let's say we want to sum them. So what you can do is you can basically group this. So let's say we split this into 4 groups. This will be group 1. And we'll call this M1, M2, M3, and M4. So these are our 4 groups of our matrix M. And what they do is, so we want to do a sum here for our alpha, and you're going to divide by the value. So essentially what you do is you say, I'm going to take the sum of this part here, so independently of the other parts. So I'm going to take the sum of M, of M1, and then I'm going to divide by NM, by the size of the entire matrix. So I'm going to call the size of the matrix S. Or NM, if this is N and this is M, then you divide by that, so S is equal to NM. And you divide by the whole matrix size, and then you multiply by G. And essentially what this is saying is this sum here is going to be 4 times, essentially what you want to do is do the operation on here by itself, and you can do something like you want to do layer normalization, just this part only, and you can do that because you can basically assume that the data in here is going to have very similar statistics to the data in like M2 and the data in M3. So you say the sum here, and then I'm going to multiply it by the number of groups, so g is equal to 4. And that essentially takes the sum and multiplies it by the number of groups. So if you just had the sum in here, you assume that the sum is going to be the same in the rest of the groups here. So this sum here is going to be the same as this sum, and this sum, and this sum. So you multiply by g, and then you divide by s. So the sum for M1 is just going to be the sum of M1 divided by the entire matrix times g. And then I'll give you this block here, and it'll give you the sum for this block. So it'll give you this here, AG. And what you do is you say that I'm going to use this sum independently from the rest of the sums here. So all of these are going to be threaded. So there's going to be a thread here, say, or maybe multiple threads. But you basically you group this, and let's just say we have a group of threads here, T0, group of threads here, T1, T2, and T3, which don't know about each other. So T0 is going to take the sum over M1, and it's going to say this sum is going to represent the sum of the entire matrix. And then you can do you can basically do the steps up here, the quantization steps here within that thread. So alpha is computed for W, for at least its part of W. I think they have the formula written down here. They do not. Or for its part of W, and then it can quantize this part of W independently of the rest, and that way you can quantize, if this was W, then you can quantize W using 4 different threads, because you have 4 different blocks, and that can be done in parallel, rather than you having to do this all by itself. So it's an assumption you make, saying that every block is going to be, like every block, the sum will just be for g times that, or the same thing for the L1 norm. It's an assumption you make, and it seems to work because you can multi-thread this, and it seems to be stable still. So essentially, this is just a way to parallelize reduction operators so that you only have to do a reduction on part of the matrix rather than the full matrix, and you get some parallelism out of it. Yeah, so they say, in this way, we can efficiently implement model parallelism with group quantization and normalization, which requires no additional communication and can scale to large language models. So it works. Now, one thing that they do is, or another thing that they do is straight through estimation, or a straight through estimator. You may notice up here that we have this thing, the sign, and the sign is not differentiable. So what do? They use a straight through estimator. And my understanding of straight through estimator is you're like, okay, we just treat this like an identity. And apparently that also works. So let's say we had a function, y is equal to x multiplied by, x multiplied by f, w, where f is going to be equal to the sign function. So f is just the sign function. Now what we need to do is take the partial derivatives with respect to x and the partial derivatives with respect to w. This allows us to do chain rule for the rest of the model, and taking the partial derivative with respect to w allows you to update w, because remember, it's in floating point 8, and you still need to update that because you need to update your weights, or else what are you doing? Might as well not be training anything. So partial y over partial x is easy. That's just f of w. Partial y, partial w is not as easy. So this is, well, it's almost as easy. It's pretty simple. So this is equal to partial y over partial f, or times partial f over partial w, which is equal to, and like I said, you treat this like an identity. So you treat the forward pass as the sign operator, but you treat the backward pass, f prime, equal to the identity, so just 1. So 1 times x, which is equal to x. Simple enough. Straight through estimator. There you go. Yeah, it says this method bypasses the non-differentiable functions such as sign and clip during the backward pass. It allows gradients to flow through the network without being affected by non-differentiable functions, making it possible to train the quantized model. Yeah, so that's what they do. Mixed precision training. So this is another interesting thing. They see that the gradients and the optimizer states are stored in high precision to ensure stability and accuracy. So they store that in floating point 16, if I'm not mistaken, the gradients and the optimizer, because you need high precision to do the updates. If you take the gradients in low precision, it can lead to a lot of issues because you're doing a lot of multiplications, and those multiplications can be unstable because you're doing so many of them. You're highly likely to have some sort of quantization error. So they keep the optimizer states and the gradients in high precision. Floating point 8 is 16, one of those. Following the previous work, we maintain a latent weight in a high precision format for the learnable parameters to accumulate the parameter updates. So they keep this here. Here. They keep this in floating point 8 and they quantize on the fly. So you keep it in floating point. I don't want that. So this is floating point 8, and you have to quantize it on the fly to floating point 1. And whenever you're done training, you can quantize it to floating point 1, and then you're good. But during training, you need this in a floating point 8 state in order to update the weights. You can't update the +1 and -1. At least I don't know of a way, and they do not either, without having it in floating point 8. The latent weights are binaryized on the fly during the forward pass and never used in the inference process. Yeah. And the learning rate. So one challenge for optimization is a small update in the latent weights often make no difference in the 1-bit weights. So what they do is they show that the model benefits from a large learning rate in terms of convergence, while the floating point 16 transformer diverges at the beginning of training with the same learning rate. So essentially, this needs a large learning rate to learn well because of the 1-bit weights. So this model, or that's the entire method. Real quick before going to the other paper, this model, where is it? Here. So the inference here, some results here. Basically, the inference is a lot less, so for accuracy. So for BitNet, the inference energy consumption for equal accuracy to a floating point 16 transformer is a lot less. So you use a lot less energy to do inference with a model of comparable energy consumption. Or that was a terrible statement. With a model of the same accuracy. So that was a stupid statement. Yeah, here we go as well. So basically, if you have the same energy consumption, so maybe BitNet is larger, but it'll give you the same accuracy. Same accuracy, better energy consumption. There you go. As you might expect. Yeah, so better performance with the same accuracy. Another thing is it's more stable with the same learning rate. So yeah, if you have some learning rate, higher learning rates, floating point 16 diverges. BitNet does not, so it learns faster and less steps, I'm guessing. Yeah, and it does quite well overall. So BitNet here, it doesn't do the best, but it does quite well compared to the post-quantization procedures. But it's also in 1-bit, while the post-quantization are usually in 16 and 8-bit. So it does quite well, while having better performance. Now, moving on, the era of 1-bit LLMs, the change is quite easy. Transition to that. So there's one thing that they do. They quantize W using a different procedure because you don't want this to be binary. You want this to be trinary, or whatever. I think it's trinary. And the way you do that is instead of dividing by the absolute max, you divide by the absolute mean here. yeah, so you divide by that instead of subtracting by the absolute, instead of, you divide by the mean. So that's the only change instead of the absolute max. Instead of dividing by the absolute max, you divide by the mean. Yeah. Oh, no, never mind. So the the original one was W minus alpha, where alpha was the mean. Here you divide by the mean. So just different. And that essentially gives you this one, or that essentially gives you this distribution here. And what you can do with the distribution is, the way I think of it is, and I'm going to assume it's a normal distribution, is you basically have, so you have this here, distribution, and you have that at 0, like that, and you're going to cut it up into 3 equal parts. Now, most of your distribution is going to be around 0, while the left and right parts are not, and whenever you quantize it, you're essentially bringing these parts here into the -1 and +1 parts, because you're doing a clip. So clip, you're rounding and then you're clipping. So you essentially just divide by the mean and then clip, round, and then clip between -1 and 1. And that gives you a pretty even distribution. If you do that, it gives you a pretty even distribution of -1, 0, and 1s, which is what you would want. And this round clip here is just round and then clip between -1 and 1. So yeah, that's what they do. Now, they don't do anything else but that. That's the only change. They also make this change here. So in the original paper, they scaled the activations before nonlinear functions, so before the GLU function, between 0 and the quantization value. Instead, they make it -QB and QB, so just normal quantization. In the original paper, they made it different from, they made it 0 and QB. So that's just another thing they do, but nothing that needs more detail. Yeah, and that's this paper here. They also, one other thing they do is they notice, well, we don't actually have to do multiplications. If we see a 1, we can just take that value. If we see a -1, we can take the negative of that value. And if we see a 0, we can just not take that value at all. And all you have to do is additions, because you don't have to do the 1 times this. You can just do additions and subtractions based off what the values are here, or just do nothing with it. And you can do that with whenever you're actually coding this on like on a low level pretty efficiently. So you don't have to do any multiplications, which is fantastic. It makes it even faster. So no multiplications and add, all you need are additions. One thing I want to mention is the intuition behind using 1, -1, and 0 is, if I have some values here, so if I had some values, x1, x2, and x3, and I have y here, then y, if I have these weights here, 1, -1, and 0, this is essentially me saying my output is going to be x1. So I want x1, or I want to remove x2, and I don't want x3. So whatever this feature is using these 3 operators. 1 is I want that, 1 is I want to remove that, and 1 is I don't want that. So the 3 operators make sense. I'm not saying it makes sense that it works so well. I'm just saying that these 3 operators make sense if you were to have 3 operators. So they don't just randomly pick numbers. It makes sense because you basically say, I want this element, I don't want this element here, and I want to remove this element here, so the negative sign. So the idea behind it makes sense. Anyways, yeah, you can do additions only instead of doing multiplications, because here you would have to do a multiplication. Here you can just have an if statement. Yeah, and they have really good results. So if we have like I said, they only go up to 3 billion. If we have a 3 billion parameter model here, and we have a 3 billion parameter model here, it does, here we go. The perplexity, it does really well. The perplexity is lower, even with 3 billion. So comparable size, and it also has a lot less memory. and the latency is a lot lower. So it's faster. We'll say it's on par, and the memory is better. Yeah, and this is the zero-shot accuracy. So the average zero-shot accuracy on a bunch of benchmarks. I don't know what these benchmarks are, but on the benchmarks they tried it at, it does better. So we'll say it's on par again. It's not significantly different because it hasn't been tested on a bunch of other models. But yeah, 3 billion, it's a lot faster, it's a lot more memory efficient, and it has the same performance. Yeah, and they show it's very efficient because you only have 1 bit and additions. So yeah, that's cool. The rest of the paper is just them kind of showing, yeah, you can do this with 1 bit and it works really well. So yeah, that's the paper. I am very curious because they only have this at 700 million, 1.3 billion, 4 billion. If this scales well, it'll be a really big thing because of how much savings you get. It also kind of shows how inefficient our current schemes are. If you can do something just as well with 3 values instead of a continuum of floating point values, that shows just how inefficient the current way of doing deep learning is. But yeah, that's the era of 1-bit LLMs and BitNet.